All right, so here last time we talked about the empirical formula, and we're going to tell you the relationship between the empirical formula and the molecular formula, right? So, for example, if I write this compound here, all right, I got H2O2, all right, what is its empirical formula?
I can't see you.
Oh, sorry. Let me fix that really quick. Okay, there we go. What is the empirical formula for this compound? Do you know? If this is the molecular formula, how do we find the empirical formula?
12 hydrogens and 12 oxygens.
Well, no. So let's do a reminder. The molecular formula is not the reduced formula. This is the molecular formula here. But the empirical formula is that, but it's reduced. So it's in its simplest whole number ratio. So here it's 2 to 2. So here we would just have 1 to 1, 1 hydrogen and 1 oxygen. And that would be the empirical formula for the compound. Okay? So the empirical formula is 1 hydrogen and 1 oxygen, where the molecular formula is 2 hydrogens and 2 oxygens. Okay? Now, let's try another one here. Here is MF, a molecular formula for a compound, N6H12O2. So, can you tell me what the empirical formula for this kind of compound is?
N3H6O1. Oh.
Yeah, very good. Excellent job. So that's the empirical formula for that N6H12O2, right? It's the reduced form. Okay? Now, you can see that there's a relationship between the empirical formula and the molecular formula, right? Each of these values down here has to be multiplied by some value to get the molecular formula values. And 2, that's right, 2. 2 is the number that we have to multiply the empirical formula values by to get the molecular formula. Okay, what about here?
Not divided by times 2.
Times 2, that's right. Also times 2. Okay, so now let's do one more. Here's a compound, C6H12O6. We talked about this compound last time a little bit. And this, let's say, is our molecular formula. What would our empirical formula be then?
CH2O.
Okay, very good. So, what's the multiplier?
6 times 6.
Times 6. Very good. Okay, so this relationship between the empirical formula and the molecular formula is very important. It helps us to relate the empirical mass to the molar mass of the compound. Now, the term empirical mass essentially means the mass of the empirical formula. How would we find that? How would we find the mass of the empirical formula?
C is 12, H is 1, O is 16. You add it all up, and then you'll get 1 mole for all of those added up.
That's right. Let me bring up my periodic table. You did a good job there. All right, my periodic table here, we can look at the molar mass for these compounds here. Carbon is 12. Hydrogen, there's 2 of them, 1 each, so that's 2. And then the oxygen is 16. So that gives us our empirical mass. Simply by adding up all of the elements in the empirical formula, that gives us our empirical mass. Okay? So 12 plus 2 plus 16 equals 32. Was that 30? What was that one? Yeah, so we call that the empirical mass. The empirical mass, 30. Right? The empirical mass. Now, there's a relationship between the empirical mass and the molecular mass And we can also find the molecular mass simply by doing the same thing, by adding them up. How do we add it up?
12 times 6 equals 72.
Very good. 12 carbons, or 6 carbons equals 72.
Plus 16 times 6 equals 168.
Okay, 168.
Plus 12 equals
12 for the hydrogen.
180.
Oh, 252. Okay, so you already took 168 was already the 72 plus the oxygen, so we just add 12. So 180. Okay, very good. 180. So we have 180 there, and we can see that there's a relationship between the empirical mass, just like there's a relationship between the empirical formula and the molecular formula is times 6. There's that same relationship between the empirical mass and the molecular mass. Right? What is it going to be there? If I take 30, what do I have to multiply it to get 180?
Yes, that's true.
It's 6, huh? Same one, same thing. Same relationship between those two. Okay, very good. So that's very crucial, because what that allows us to do is once we have the empirical formula and we can find the empirical mass, and from that we can get the molecular mass. All right. So if we want to determine what the empirical formula is, first we're going to use our mass of the given material, right? And then we can find the empirical mass. So, for example, here's some compound. Let's say we did an elemental analysis and we found out how many grams of carbon, how many grams of hydrogen, and how many grams of oxygen are in this compound, okay? Let's say we found all that out inside that material. And, why would you want to do this? Well, sometimes you get a spooky powder sent to the President of the United States. And you need to find out if this powder is poison or not. And we need to know the empirical formula to find out if that powder is poison. It might just be flour, but it might be something like anthrax, right? Some poison that's going to cause problems. Okay? So, how do we determine that? Well, we have to know how many grams of our material we start off with, and once we get the grams of material, and let's say here we have carbon, hydrogen, oxygen in there. Let's say we have 12 grams of carbon. Let's see how much. 4 grams of hydrogen and 16 grams of oxygen. Right? So let's say we have 16 grams of oxygen. Now we know how many grams of each of these, not 1 gram, 16 grams of hydrogen, oxygen. So now that we know how many grams of each of these, can we take these values just like this, grams of carbon, grams of hydrogen, grams of oxygen? Can we take these values and just stick them on the empirical formula? So for example, can we take these grams and put it directly onto an empirical formula? Like this, could we call it C12H4O16 using the grams of material? Can we put that on there like that? What do you think? Is that okay to do? So this doesn't make any sense. We can't do this because the carbon, hydrogen, and oxygen here are moles. That's what the empirical formula is. That's supposed to be moles. It's not supposed to be grams. So when we have an empirical formula, we don't use the grams of material, but we can take those grams and we can convert those to moles. We can convert that to moles. So, for example, if I started with my 12 grams of carbon and converted that to moles, then I could find out how many moles that X actually is, right? So if I have 12 grams of carbon, as we said over here, and I want to get that to moles of carbon, right? Grams of carbon up the top left. What do I need to have in here so I can get moles of carbon?
1 gram.
Grams of carbon down here, is that right? And what's up top?
Moles.
Moles of carbon. Very good. So, how many? How many? 6? 600? I need to use the periodic table, don't I? How many grams of carbon? That's right, 12 grams of carbon for every mole of carbon. Very good. So I can put, where's the 12 go? At the top or the bottom? Bottom, that's right. 12 goes on the bottom. 12 grams of carbon for every mole. So I see that I have to take 12 divided by the 12, and that will give me moles of carbon. Okay, how many moles am I going to get?
That makes it 12. No, 1.
1. 1 mole of carbon. Very good. Excellent job. So that was my grams of carbon, and now I'm going to do my, moles of carbon. Now I'm going to do moles of hydrogen, right? And I set it up the same way, just like that. And the goal is, of course, to find the X, Y, and Z in my empirical formula, because those values are moles, not grams, okay? So I go to moles of moles of hydrogen. I need to start with my 4 grams of hydrogen.
Moles of hydrogen. Oh, moles of hydrogen. There's 4 hydrogens.
For what of hydrogen?
A gram.
Yeah, 4 grams of hydrogen. Very good. And now I need to get to moles of hydrogen. How am I going to do that?
And then grams goes on the bottom right.
Yep, grams of hydrogen down there. What's on top?
And then moles of hydrogen going.
Very good. Moles of hydrogen on top. Now, do we know the ratio? What are the numbers that go with this?
4 grams equals 1 mole.
4 grams of hydrogen?
No, 1 gram.
That's right. That's right. It's just the number on the periodic table, right?
From the periodic table.
That's right. 1.008 grams for every mole. Good. Excellent. Okay, so oxygen. Let's do the same thing for oxygen. We need to identify moles of oxygen, just like we got moles of hydrogen and moles of carbon so far.
4.
Yeah, 4 moles of hydrogen here. So I have moles of hydrogen, moles of carbon, and now I need to go for moles of oxygen. So far, though, I have C1H4, right, because those are the moles, and that's what the empirical formula is. So now I just need to get moles of oxygen. So how many moles of, or what do I start with for that? How many grams do I have?
16?
Yeah, that's 16. 16 grams of oxygen. And then I go from what? How do I get to moles?
Well, the grams on the bottom right.
Grams on the bottom right, that's right.
And moles on the top.
And moles of oxygen up here, very good. What numbers?
16 grams. 16 grams equals 1 mole.
That's right, very good. It's on our periodic table, right? So we just take that 16 there, and that's how many grams you need to get a mole of the material. So 16 grams for every mole. And so I end up with 1 mole of oxygen, and our empirical formula then is CH4O. And we got that information again from the mass of carbon, hydrogen, and oxygen in that equation, or in that sample. Okay, so here is another one. This sample contains 2.012 grams of some compound. All right, 2.012 grams of the compound. Here's my sample there. And it's a little bit of a different problem here because I'm not told what the percentage of the different components are, but I'm told that I have 0.522 grams of nitrogen and 1.490 grams of oxygen. And from that, we want to calculate the empirical formula. So if I write down 0.522 grams of nitrogen, 1.490 grams of oxygen, right? So how can I find the moles of material? Because that's what the empirical formula is.
Nitrogen is 14.
Okay, so I'm going to start with an equal sign.
0.
Why don't you show me how to do it on your computer there? All right, so give yourself a little more space there. Okay, a little more space. So yeah, then we start with our 0.522 grams of nitrogen. All right, and we're trying to get it to what? What's over to the right there? Grams of nitrogen, you got there, okay. Does that say grams of nitrogen? 0.522. All right. So we need to go from grams of nitrogen on the bottom, right? To what? What do we need to go to on top? What are we trying to get to on the right? Moles of what? Moles of what? Nitrogen. Very good. Moles of nitrogen. So we got grams of nitrogen on the bottom, and we're going to try to go to moles of nitrogen. How do we get to moles of nitrogen?
Yeah.
We use the periodic table, right? Yeah. So 14 moles of nitrogen on top. How many moles of nitrogen? What's the relationship for grams of nitrogen to every mole? 1 mole is 14 grams. Very good. That's on the periodic table. So if we take our 0.522 divided by our 14, that'll give us moles of nitrogen. Very good. Okay, 0.0372 moles. Very good. 0.0372 moles of nitrogen. All right, now what do we do for the oxygen? Good. What do we want over there? We want moles of oxygen. Very good. And what do we start off with? 1.490 grams of oxygen. Okay, good. Now we got to go from grams to what? Okay, grams of oxygen on the bottom. 16. Yeah, very good. 16 grams for every 1 mole of oxygen. All right. So in the calculator, all we got to do is take our 1.490 and divide it by our 16, right? So I got 0.093125.
Yeah.
Okay, very good. So 0.093 moles of oxygen. So now we're ready to look at the empirical formula, right? So we have nitrogen. Our number of moles is 0.0373. Oxygen, 0.0931. And if we know the moles of material, moles of the elements, moles of nitrogen and moles of oxygen, they can be written down here as the X and the Y on an empirical formula like this, right? So nitrogen 0.0373, 0.0373, and then oxygen 0.0931. Now, what do we do to make that a whole number? We can't have an empirical formula like that. We have to have it a whole number. What do? We can divide them both by what? By the smaller one. So which one, what am I going to divide it by here? 0.0373, right? That is our smaller one, okay? So if I do this one on the left, I know I'm going to get 1, right?
1.
Yeah, 1. So on the right there, what do I get? What do I get if I put 0.0931 in my calculator and divide by 0.0373?
0.0931 divided by 0.0373. 0.4949.
Okay, essentially 2.5, right? 2.5. Now, unfortunately,
Right.
2.5 is not a whole number. How can we get it a whole number? Because empirical formulas need to be in whole number ratios. So how are we going to get this into as a whole number here? Well, what can I multiply 2.5 by to make it a whole number? 2, right? If I multiply by 2?
Yes.
Yeah. 2, if I multiply by 2, what will it be?
Yeah, and then you have to make nitrogen 2 too.
Yes, nitrogen has to become 2 and oxygen becomes 5. Very good. So that is our empirical formula from the excuse me, from the masses of nitrogen and oxygen, right? N2O5 is our empirical formula. Okay, very good job. Let's take a look at this one here. From those masses, we were able to convert those grams of material to moles of material, and then from those moles, we got we simplified our values into whole numbers, and that whole number ratio, the simplest whole number ratio of our different elements in our compound, is called the empirical formula. Now, as we said before,
Can we
there.
pause?
As we said before, the empirical formula is the simplest whole number ratio, but there's a multiplier between the empirical formula and the molecular formula. The empirical formula is the simplest ratio, but if you multiply it by a multiplier, you get the molecular formula, right? And if you take the molar mass, like we did before, and divide it by the empirical mass, you can identify what that multiplier is, right? Because the empirical mass, which is just the mass of the empirical formula, is also the molecular mass divided by the multiplier, right? So if you knew the molecular mass from the molecular formula, maybe, right, you could identify the empirical mass, and you could also identify the multiplier there, the N value. Okay, very good. So in this case, glucose, the molar mass was 180, the empirical mass was 30, 180 divided by the 30, and that gave us our multiplier, which is 6. Okay, so this question says that I have a compound named hydrazine. Its empirical formula is NH2. Its molecular mass is 32, and what I'm looking for here is the molecular formula. So I know its molar mass. All right, let's get a new piece of paper here. I know the molar mass is 32, and I know the empirical formula is NH2. All right. Is there any way I can get the empirical mass? Well, let's start off with the empirical formula. What is it?
Oh, wait, empirical NH2.
Yeah, right. Empirical formula. So we just got to search through the problem there. NH2. And what then is our, whoops, not our empirical, the molecular. I better start over here. Empirical formula is NH2, all right? And some multiplier will give us the molecular formula. But we don't know what that multiplier is, all right? Now we know that the relationship between the empirical mass, let's find out, what is the 32 here?
Hydrogen is 1. 32 is all of them combined.
32 is the molecular mass, right? Right, 32. What is our empirical mass? So our molecular mass, we're told, is 32, but how do we get our empirical mass? What is our empirical mass? Well, isn't it just so we know that this multiplier exists, and it's the same multiplier here as it is over to the right.
Right.
How do we get the empirical mass?
Why does it say oxygen?
Oh, I think it's just down there for the next
Yeah.
problem. The next problem. Yeah, the next problem has oxygen in it, so that's why it says oxygen. But you can just ignore that for now. Where do we get the empirical mass?
There's 2 hydrogen. So
All right.
that's 2.
Yeah, so we add up the masses here, right?
14.
14
16.
plus 2, 16. Very good. 16 is the empirical mass. Very good.
2.
Yeah, look, we see our multiplier is times 2. So therefore, the same multiplier exists going from the empirical formula to the molecular formula. So what should it be? N2H4. Very good. So that tells us that our molecular formula is N2H4. Fabulous job.